Hello viewers, today we are going to see about horizontal oscillations of spring. Consider a mass M attached to an end of a spiral spring which obeys Hooke's law, whose other end is fixed to a support as shown in the figure. So this is a spring. A solid object with mass m is connected to the one end of the spring. Another end of the spring is connected to a fixed frame structure. That is, it will not move, and it a fixed support. The body is placed on a smooth horizontal surface. So if you look into the diagram, this mass, this body is placed in the horizontal, and we are going to pull this mass in the horizontal direction. We have another case, vertical placing the load vertically also. Let the body be displaced through a distance x towards right and released. So now what happens is, this mass is pulled to a distance of x. So I measure with respect to center and then released. So what will happen is, this mass will try to cross the mean position, go this side, and then try to oscillate around the mean position. It will oscillate about its mean position. The restoring force acts in the opposite direction and is proportional to the displacement. That is, if you try to pull this mass this side, because of the restoring force, it is acting in the opposite direction. So that, therefore, we can write restoring force F is directly proportional to the displacement. In this case, the displacement is from this point to this point. So the distance is x. Now we will introduce the constant of proportionality. F is equal to minus kx. We introduce this minus sign just because the forces we apply is in this direction, whereas the restoring force is in the opposite direction. Therefore we introduce the minus sign. K is the spring constant. Okay, K is the spring constant we have seen in the earlier videos. Now by Newton's second law, we have force is equal to mass into acceleration. Okay. Therefore, this is also force pertaining to this condition, and by Newton's second law also can be applied for this condition. Therefore, this force and this force can be equated. Therefore, NA is equal to minus kx. Now, acceleration, from this acceleration is equal to minus k by m into x. So this is the new relation we have for acceleration. In terms of spring constant, mass of the object, and the displacement x. Okay. So already while we deal with simple harmonic motion, we got the answer for acceleration, which is minus omega square x. This we have derived in explained in our previous videos. Please go through those videos. In that we have derived for acceleration, which is given by minus omega square x, where x is the displacement In that case, we will be dealing with vertical displacement, so y will come. So anyhow, it is going to be displacement only. Now what you do is, here also acceleration, here also acceleration pertaining to this condition. So we can equate these two acceleration. Therefore, minus omega square x should be equal to minus k by mx. So we are equating these two equations. So this x and this x gets cancelled. Minus sign gets cancelled. And therefore we have omega square is equal to k by m. Now what is omega? Omega is equal to square root of k by m. We all know that omega is equal to 2 pi f. Omega is equal to 2 pi f, where f is the frequency. In textbooks and all, this f is is given as n. So I'll be using f as frequency, which is equal to square root of k by m. Now we want frequency. Frequency is equal to 1 by 2 pi root of k by m. So the frequency of oscillation of this spring centered around this mean position is given by 1 by 2 pi square root of k by m. Now if we are interested in finding out the time period, so we have the well-known relation between frequency and time period. So t is equal to 1 by f. Now this is equal to 1 divided by 1 by 2 pi square root of k by m. So t is equal to, this 2 pi will go to the numerator. Similarly, the square root m by k. So this is the time period of the oscillation. So t is equal to 2 pi square root of m by k. So the frequency of oscillation, the 2 pi is constant, square root of k by m. So if you want to increase the frequency, the mass should be if mass decreases, frequency will increase. That means if you use a lighter object, lighter mass, so the mass decreases, frequency increases. Similarly, the spring constant k increases, frequency increases. The vibration frequency will increase. If this is increased and mass also, so we can increase the frequency greatly. But for a particular system, for a particular material, this is roughly is going to be a constant of the particular material, spring constant. So we cannot do anything after choosing the material, nothing can be done with k. So the frequency of the oscillation is inversely proportional to the square root of mass of the object. That's the significance of this lecture. Hope you have understood this topic about horizontal oscillations of spring. Thanks for watching this video. Please watch earlier videos connected with oscillations, the basics of displacement, velocity and acceleration. Thanks for watching. Nandri.